Thanks. So I'd like to thank the organizers again and for giving the opportunity to present this work. Though my title suggests I'll be talking about how to compute the phase space integrals, but I also give the phenomenological motivation behind this. So basically, how to compute the QCD electric correction to Z version production. And this work has been done in collaboration with Roberto, Federico, Ilario, and Alessandro. And we study all the integrals, including virtual loop integrals and also the phase space integrals, which are required for NNLO mixed QCD electric correction for Z boson production, which is basically a part of full Drellian contribution. And you don't basically need why we want to compute the Drellian correction to such precise order. I mean, this is one of the standard candle process for detector calibration, and there are so many physics motivation behind it. So to name basically the three of them is that detector calibration and then precise measurement of various electric parameters, for example, W boson mass and sine square theta. Additionally, many BSM physics, they mimic the same final state. And so there is a possibility to find BSM physics behind this same final state. So we need precise prediction for Drellian. This has already motivated us for quite a long, and we have quite a good predictions, mainly from the QCD side for Drellian. And recently there has been works by Dulert and Mistelberger to obtain the full NQLO QCD corrections, which takes us to the most precise limit. Now, when we are going so much advanced in QCD side, whether we need the NNLO QCD cross electric correction or not. So, and additionally, that hadron colliders are aiming for per mil precision, and QCD corrections at NQL also gives us almost per mil precision, and to match that accuracy, so whatever we can get, so which any higher order corrections which gives us per mil precision we should include. And inclusion of such higher order contributions also reduce the uncertainties which comes from unphysical scales, namely renormalization and factorization scales. Hence, the higher order corrections are very much important. So if we just look at from naive argument of coupling strength, that is comparing alpha s cube with alpha s alpha, we see that they are almost same. And so we expect similar contribution just from this naive argument. However, in some phase space points, fixed order electric corrections can become very, very important because they contribute through the large logarithmic enhancement, which can be weak logs, also the QED logs, both are Sudakov types. And we need to know them exactly so that they can be resummed. And these resummed predictions actually helps us to have a better prediction or more precise prediction. Next point comes when we see that for the W mass measurements, the NLO electroic effects are quite large. And we also know that almost any NLO QCD corrections are large. So this mixed QCD cross electroic will be the NLO QCD on top of NLO electroic. So if we aim for less than 10 MeV precision for W mass, this is a must needed. Additionally, the appearance of photon induced processes, that means we have new type of process, we have photon in the PDFs, which opens a new channel. So all these physics motivations are quite important and really motivating to compute this process. So to summarize that if we want to achieve less than 10 MeV precision for MW, which is most important part, we need the lepton distribution at per mil level, and that implies this process needs to be computed. And then I have another slide on a different note. I mean, we know that when we compute Drellian, we use the experimentally measured values, for example, Fermi constant, W mass or Z mass as input. And this input choice, we have a general choice for G mu scheme where we consider the Fermi constants mw and mz. However, for theoretically speaking, we can also consider alpha and mw mz as our input. So what does it differ then? The difference is that there is a relation between G mu and alpha, which gets corrections from one loop electroic and then so on, mixed QCD electroic corrections and so on through delta R. And when we are computing pure QCD corrections, that means we are neglecting the contributions from delta R. And so this is leading order in electroic. And from this relation, we can compute alpha through the values of G mu and sine theta and mz, which are experimentally measured. And this alpha value, which is denoted by alpha G mu, and the experimentally measured alpha value, which is denoted by alpha 0, they differs by 3.53% at leading order in electroic, at leading order of this equation. And that is quite important because using these two schemes, because of this, we have a difference in our leading order result or NLO QCD result or any NLO or any QCD correction we do thereafter. And the difference remains 3.53%. And we can see that if we have electroweak corrections, just electroweak corrections on top of leading order, the difference comes down to 0.53. So that means we need to incorporate electroweak corrections. And then you say, okay, we are fine with NLO electroweak, then we include all the QCD corrections. Now that's not good because then we have the QCD corrections, for example, delta 1, 0, which is NLO QCD, and then there is nothing to suppress the contributions coming from delta 1, 0, which is making a difference for G mu and alpha 0, and the difference increases to 0.89. So that clearly implies that we also need the mixed NNLO QCD cross electroic corrections. And I hope that's quite well motivating. So after that, let us fix the notation, which you all know, that we have the total cross section, which has to be convoluted with the with the PDFs, with the finite PDFs convoluted with the finite partonic cross sections, and they are expanded. The finite partonic cross section sigma ij is expanded into alpha and alpha s, and we compute sigma 1 1, and that's for the notation. So then I come to what are the contributions and how we compute them. So purely at two loop level, there will be mainly three type of contribution. So one is virtual. So there will be virtual two loop diagrams where there will be one or two massive bosons or massless, including photon, and one gluon. So these kind of diagrams will contribute. Then there will be one loop diagrams with one emission of real particle, and there will be double real emission. So with these three kind of contribution, that they will be there in pure NNLO level, and there will be additionally contributions from one loop. The loop integrals we have to integrate, and finally we will see that we find the result in terms of constants because we are considering the on-cell Z boson production. So the constants will be multiple zeta values and cyclotomic constants, and the phase space integrals we have to integrate the momenta of the real emitted particles. They are often performed numerically, but we are trying to obtain the inclusive production cross section. So we require an analytic expression. And finally, when we are done, we will see that these contain standard HPLs with different letters and also elliptic polylogs. So here now, for our convenience of the calculation, we divide the whole process in basically four types, considering the different vector bosons. So one is when there is photon, that is simpler, and that we don't talk about hereafter. Then there can be a single Z propagator in the loop. Note that we don't include any Z boson or any massive boson in the emission. So whenever we have emission, it's either a gluon emission or a photon emission or two quark emission, because emission of massive boson is infrared finite, so can be treated as a separate process. And then there is the division EW1 when we consider only single Z propagator, EW2 when we have single W propagator, EW3 when we have this WWZ vertex. And note that we can treat them separately, which is better for us, easy for us, convenient for us. And QCD QED is gauge invariant and finite. EW1 is separately gauge invariant and finite. But when we compute EW2 and EW3, we have to compute them together because together they're gauge invariant and finite. So, and the generic procedure is quite well known. You draw the diagrams using QGraph. So, uh, and then use the form routines for several or different algebraic manipulations or the low range Dirac and color algebra. If we have the, when we have the phase space integrals, that means we have a delta function. We use the reverse unitarity technique to write down all the deltas in terms of propagators with I epsilon prescription. And the advantage of doing this is that now we can use all the techniques for develop for loop integrals. So for example, when we go next, that decomposition of the dot products to obtain the scalar integrals, and then we use the IPP relations. Once we use the IPP relations and we find the master integrals, and finally we solve the master integrals using differential equation, and that is the generic procedure to obtain all of them. So let us see how we do them. So before that, I make few comments. So first comment is on the method of differential equation. We do not use canonical form for the system of differential equations. Uh, so when we are not using canonical form, we are expected to find coupled differential equation, which most of the cases it's maximum 2 cross 2 or 3 cross 3 matrices, which we decouple them. For 2 cross 2 it is easy, but for 3 cross 3 we use one of the following uncoupling algorithms to make the decoupling easier. So either Zurcher or incomplete Zurcher or Abrahamov-Zima. And on the dependence on MW and MZ. So for example, if I go back this kind of diagram, then we have WWZ vertex, and or even this kind of diagrams where we have a W inside and a Z production. In that case, we have two scales, which is difficult to handle at the moment. So what we do, we expand all the propagators, basically the integrand containing MW around MZ with delta M square. So once we do the expansion, and we can treat all the integrals as a single mass integral. So basically it boils down to single scale problems, which is much easier. And through the expansion, we can get a nice phenomenological result. So whenever we have two mass, we do the expansion of MW around MZ. And I introduce more notations. So we have the variable Z defined as M square over Q square. And at various points, we need to do variable transformations to T, rho, or W, you will see. And after doing all this transformation, we only have few letters. These are the letters that appear in whole the process. And among them, they are the third and sixth and fourth root of unity. So with everything defined, let us go to the computational details for starting from the double virtual. So for the double virtual case, we have two different kind of topologies. So one is when we have a single massive line inside, everything is massless. And another case when we have two massive lines inside. So for the first case, we define the variable x. And for the second case, we define the Landau variable xl. Now, to take the help of differential equations, we compute the integrals considering offset z so that we can use differential equation. And the boundary conditions are easily obtained for x equals to 1 and x else equals to 1. And the result can be written in terms of HPLs with alphabet -1, 0, 1, and 6, 0, and 6, 1 only. So this can be obtained for the offset z. Now the trick is, or the main part is to take the Onsel limit to achieve the Onsel result. So for EW1, this is simple because we have MZ inside and we have the Z production here on Z. So the limit is basically x to minus 1, which is simple. For EW2, we have two cases. We have in case of X, so when you have a single W propagator, we have to do the series expansion corresponding to limit q square going to mz square for X. And for this case, we also cannot take the limit XL going to this. Rather, we have to do a series expansion around delta m square, because at the end we want a precise result and we have to do the series expansion of MW around MZ. So once we perform the series expansion, we have HPLs with arguments what we saw earlier, minus 1, 0, 1, 6, 0, and 6, 1, but sorry, with the letters that we saw earlier, but with argument R2. And that's a little bit of problem because if we have HPLs which are dependent to each other, we will not see in the final stage the analytic cancellation of the poles, which is very important for us for inclusive production. So we have to reduce all the HPLs to a basis. So we chose the basis introduced by Hen and Smirnov. So finally, we write down all the HPLs with minus 1 in the argument and with R2 in the argument, and with all the letters minus 1, 0, 1 and 6, 0, 6, 1 to the basis chosen by Hen and Smirnov. And this reduction of the basis is very much important for analytic cancellation of singularities. So next we go to the computation of real virtual. So for the real virtual case, we have different kind of topologies when we have QQ initiated states or work clone initiated states. But the general procedure is quite same. Use the reverse unitarity, get the IVP reduction rules, get the master integrals, differentiate and solve the differential equation. Excuse me, can you see my cursor?
Yes, we can see it.
Okay, sorry, and there is a glitch. But now the problem is that we have few square roots. Well, you say that, okay, we go ahead with the square roots and we define our iterated integrals, which is fine. But as we know that the numerical evaluation of the iterated integrals with square roots is not efficient. So we need to rationalize them. And as Roman was saying in the earlier talk, sometimes it is better to use different rationalization rule and make subsystems so that we have more than one argument or one variable. So, and the advantage of doing that is that we have good letters, and in the end we need a first numerical evaluation. So if we have good letters, that is much better. So that's what we do. We divide this system into pieces, and so for example, we take 1 minus 1 and 0 with the cyclotomic ones, that's the system, and then 1 minus 1, 0 with these square roots, that's another system, and 1 minus 1, 0 with this one, that's another system. And then each system gives us different arguments using the transformations to Z, rho, and W. So once doing that, I repeat that we have our result in terms of HPLs with only these letters, which helps us in very first numerical evaluation. Let's take an example. For example, we have simple integrals J1 and J2, where J1, the solution of J1 involves a square root letter, and the homogeneous solution of J2 contains standard kernel, but it depends through the non-homogeneity to J1. So first what we do, we try to avoid the square root letters or coming to the single pole of the whole matrix element. So because we know that our single pole is have a simpler structure in HPL. So whatever square roots are coming, or the other square root later converted to different arguments, they are coming to single pole, they will be cancelled eventually. So we try that beforehand. So we try to find a combination of integrals j0 such that a combination of integrals j0 in terms of j1 and j2 such that we can solve j0 for the poles at least uh, with simpler HPLs. So the combination becomes the differential equation of J0 becomes like this, where the non-homogeneity depends on J1, which is proportional to epsilon. And then, of course, I mean, if we have a square root later in J1, say at 1 over epsilon, we lose it at J0 minus 1 at the poles, but we of course have it at J0, 0. That is the finite piece of J0. So this way, we avoid all the square roots, or we move all the square roots or the bad looking HPLs to the finite piece. So, and our poles, the single pole of the whole matrix elements remain clean, and hence allowing us for a nice cancellation. Now, the next, uh, when we solve J0 for the finite piece, which of course have the square root pieces, we perform the variable transformation as we discussed earlier. So we divide the non-homogeneous piece in two different pieces, one depending on the variable z, another depending on the variable w, which comes from the rational transformation of the square roots. And then we treat them separately. And finally, we have our results. So the results looks like this. And notice that we have j1 minus 1, which is depending on w. And we don't need to compute j1 0 because of our useful combination. For j0 0, that is again for j0 minus 1, the answer is simply in terms of HPLs with z, which is simple. And for j0 0, now we have the answer in terms of the mixed variable. We could have written everything in terms of w, but in that case, we will lose, for example, these pieces. These pieces will be translated to variable w. Now, the bad thing about losing these pieces is that, I mean, there is a singularity at half, but this is not there in our matrix elements. This is pseudo singularity. And obviously, there will be other terms from other integrals. So there will be same term from other integrals, which will eventually cancel all these singularities. And we want to get it done analytically. So that's why this division of variables is quite important, because then in the end, we have the finite answer, which doesn't have any spurious singularities or pseudo singularities. So that's why we make these little tricks. So when we compute the real virtual integrals, we also need to compute the boundary conditions for that. So the generic idea is quite simple. Compute the exact solution of the one loop integral which contains the massive lines, and then take the soft limit. Once we take the soft limit for the exact solution, we can compute the two body phase space integral. This has been known. But for the massive boxes, we take a different approach. So for the massive boxes, first we assume a general structure for the massive boxes in terms of T and U. So when we take the soft limit of any one loop integral, what we generally look for is the structure of T to the power n epsilon. So these kind of structures, they actually contribute to the phase space integral, or to the soft limit of the phase space integral. So when so we assume such a structure by looking at the massive box, but the coefficients obviously is unknown. Now with the massive box, there can be two real virtual integrals. So one is called 6den, and other is with 7den. How we define them? So the T propagator in the bond, so if we go to the graphs, so there is this T propagator in the bond connection, and without or with this one. So without this one is called 6den, and with this one is called 7den. And so we define them, and we can obtain the soft limit of the 6-dimensional integral using IBP reduction rules. We can also obtain the soft limit of the 6-dimensional integral using our assumed structure, and then we compare two to get the unknown coefficients, and then we are done. And then we take the known coefficients now to compute the 7-dimensional integrals. So this is much comparatively easier to compute than computing the hypergeometric function and taking the sublimit. Okay, now I come to the computation of the double real. So again, the same process, reverse similarity, IBP, and I don't repeat. And here we have another different set of kernels. Similar to real virtual, we write the system in a separate dependent variable, in a dependent variables and separately treat them. As a result, we have some new letters here, but the calculation is almost similar to real virtual. However, when we treat the double real, we face a subsystem which is elliptic, a 3x3 subsystem, which is not first order factorizable, giving a set of 3 elliptic integrals I1, I2, I3. And as you can recognize immediately, the homogeneous part of this one for the virtual case was studied by Aglietti, Bonciani, Grassi, and Remedi to obtain the results in terms of elliptic integrals of the first kind. And recently by Brodel, Dulert, Penante, and Tancredi to obtain the result in terms of EMPLs. So in our case also, in each order of epsilon expansion, the 3x3 system reduces to 2x2 and 1x1 subsystems, and they can be solved with standard HPLs for the poles. So when we have I1, I2, I3, actually I1 and I2 doesn't have pole in our definition, and I3 has one single pole, which is simple HPL. And then the finite pieces have elliptic polylogs. However, there is a problem because the IBP reduction introduces a 1 over epsilon in the coefficient of these integrals. So that means we need to compute it up to higher order in order epsilon. But the main problem is that the finite part of the integrals which contain elliptic polylogs, they contribute to the single pole of the whole matrix element. So we can easily expect that this contribution, these 3 contributions coming from 3 integrals, they should conspire, and this should conspire to some simple HPL, because all the other integrals contribute to single pole of the matrix element. They are simple HPLs. And finally, we need cancellations. So we've tried to find a combination of the elliptic masters, and we find I0 as a combination of I1, I2, and I3. And the differential equation order by order for I0 is ordinary for at least the pole and the finite piece. So we can solve it and get the result in terms of HPLs. So we are done in some part, because using I0, we can solve the poles, we can get the cancellation of the single pole, and now we have to compute for the rest to obtain the finite part. But we get the analytic cancellation of the poles. That's the first step. Of course, when we try to compute the finite part of I0, they cannot, this cannot remain independent of I2 and I3. I mean, this has to appear somewhere. And so they contribute to EMPLs with finite part of the matrix element. Now, to avoid the numerical evaluation of the EMPLs, we expand in logarithmic series. So we perform series expansion for I2 and I3 around z equal to 1, half, and 0. And we impose the initial conditions in z equal to 1 and match the different series in intermediate points. Now for I0 to compute, we again take the procedure as discussed in real virtual case. So we compute part of I0 as exact form, which is basically is dependent part, which depends on HPLs in closed form, and the rest, which depends on I2 and I3 or EMPLs, we compute them in expansion. So why do we do that? Because we see that these are the expansion results. So I1 in blue, this is I2, and this is I3, and the expansion results are quite nice, or they're quite nice. And for the expansion result of I0, which the part which is expanded, that is also quite nice. So for numerical evaluation, they're quite helpful. And the exact closed form of I0, that contains some HPLs, which contains all the logs and divergences. So they also cancel with other pieces, so that For the rest of the result, which is closed form, we also have a nice numerical evaluation. So with that, now I also need to compute the boundary values for the double real, which is taking basically the soft limit to z to 1. For that, we scale the momenta, the outgoing momenta L1 and L2 with 1 minus z. And eventually, when we do that, all the scalar products will be scaled as 1 minus 2, 1 minus z, or 1 minus z square. This is basically the prescription which was taken for NNLO hex calculation. Now, for Z boson production, all the momenta, all the propagators which appear with the mass can be easily parameterized. Using this parameterization can be shown that they do not contribute to the soft limit. So uh, we can easily compute all the soft limits of the integrals containing the massive lines through the ones without without the massive lines. So once we compute all the such double real, real virtual, and double virtual integrals, we use them in our matrix elements and obtain the result, the unnormalized result. Now we need to renormalize them. The renormalization of electroic sector is quite involved. Now for us, there is no alpha s renormalization. The quark wave function need to be renormalized, and we use the Onsel scheme. For the rest, for the neutral current vertex and everything, we use background field gauge, with the advantage that the vertex and the propagator contributions are separately UV finite, so we compute them separately. Once we find the UV normalized result, we obtain the finite partonic cross section, which now needs to be convoluted with the physical parton densities. We have two parallel photon codes to obtain our numerical result. In one code, we use harmonic sums and GNAC to evaluate all the sigma ij separately, and we save them in grids, and then use interpolation routine. This is quite fast because of our compact structure. We can evaluate each sigma ij in few minutes for quite a good precision. And we also use in another program, we also use handy G at the during the integration to evaluate sigma ij. And finally, we obtain our results. So before presenting the final result, I want to show you the specific sigma ij uh, because of some interesting point. So one interesting point to note is that the behavior of the contribution from AW1, that is the Z, is almost similar to the NLO QCD. That's bit expected because we can almost say like this is factorized. This can be the structure we look at coming from the soft gluon, and for both cases, for QCD, NLO QCD, and EW1, when there is a single Z boson, the function appearance of the functions are same. So we see a similar pattern in both cases. Another interesting point, we note that in the inset, if you find that there is a kink at Z equal to 1/4, and that is expected also because that suggests the diversion production threshold. So there will be one diagram when with the Z particularly that QU bar going to Z and decaying to UU bar again. And we can have a cut at that Z and the Onsel Z. So indicating that this is the diversion production threshold, and that we can see in the particular matrix elements. So finally, I'll come to my results. We have the NNLO QCD result pointed here, and finally, when we have the total cross sections added, we see what we looked for, that the difference between these two schemes really the spread reduced to 0.23%. So that is the effect of including the mixed NNLO QCD cross electric corrections. And obviously the total correction is again as expected. This is almost per mil level to the bond. The NLO QCD QED correction is like 0.03% of the bond, while this mixed one is larger. than the QCD-QED by almost a factor of 3, and thus gives us a per mil correction, which is quite important. So I'll come to my summary. We computed the full mixed NNLO QCD electric contribution to Z boson production, which is an important ingredient to the full Drell-Yan. We use all the methods of loop computation for phase space integrals. We have computed the two loop virtual and phase space integrals with massive lines, and the solutions are obtained mostly in terms of HPLs and several constants and multiple zeta values and cyclotomic HPLs at 1. The contribution from elliptic polylogs are obtained as series expansion. Then we have performed cross checks analytically and also numerically with the available QCD-QD result. There has been also recent computation by Monte Carlo, and we also agree to expected numerical accuracy to that result. And few remarks that the computation of the master integrals for virtual and phase space integrals is challenging, and it is only possible due to current development in loop computation. Understanding the polylogarithms in detail really help in such calculation. For example, when we saw for the double virtual case, when we are trying to reduce the polylogarithm constant to a basis, it was very much necessary to achieve the analytic cancellation of the divergences. Also, in between, in case of real virtual and double real cases, there are such cases which also appear, and for them to see the analytic cancellation, this is quite important. Understanding and the manipulation of polylogarithm functions, transformation of variables in great detail also helps us to achieve a compact solution, and because of this now we can easily evaluate the numerical solution, or we can easily get the number in few minutes because of the compact answer. So I still have some more time, so thank you for your attention.
Okay, thank you very much. I suggest that we take 2 or 3 seconds to unmute everybody, and then we give Narayan a round of applause. Okay, so we still have a bit of time, so we have time for questions. I see there's a first question by David. David, please go ahead.
So congratulations on this very sustained piece of analysis. It's very impressive. Would you go back to slide 11, please? So with deference to the barking dog, I have a historical remark to make about the appearance of the golden mean in your calculation. We had a very nice remark by Roman going back to 1934. The first example of multiple polar logarithms of the golden ratio, square root of 5 minus 1 upon 2, date back 280 years to John Landon.
Okay.
And when I was dealing with polar logarithms of the sixth root of unity, which you have everywhere in your equations, Deligne suggested that there were no conjectures for fifth roots of unity. But what I was able to find is that if you go to the real subalgebra of fifth roots of unity, which is the golden mean, then there's a beautiful mathematical structure. And I'm absolutely delighted to see 280 years later that occurring in practical calculation and high-energy physics. It points to the unity of mathematics. And I have an article on the archive entitled Multiple Landon Values, where you can find more about John Landon's remarkable work.
Thank you. Thanks for the information.
Okay. More questions for Narayan? So maybe I can ask a question. So Narayan, so you commented at the beginning on the NNLO, and then you said that your calculation is in some sense complementary because you include QD radiation, and there's also the question about the scheme you necessarily use for the electroweak coupling. And now imagine I wanted to get the best prediction that is on the market. I would want to compute our N3LO calculation with your mixed QCD electroweak. What would I need to do? Because I'm wondering in specific, well, one thing is the scheme that is used for the randomization, but in particular the PDFs, because what we usually do is we use PDFs
Yeah.
that are inclusive in QED.
Yes.
So what would we need to do to
I did
combine
not
them?
make comment on this because it will be too much probably, but I mean, when we use, for example, pure QCD PDFs and then QCD, Lux QED PDFs, there is a hell lot of difference. So, I mean, when we use, for example, NNPDF QCD and NNPDF QCD QED, and that difference is also quite large. So, when we, I mean, the contributions from photons, they are there. So when we are including the QCD, QED, and QCD electroweak corrections, we should consider them in the PDFs. And also the contribution, I mean, there is no radiation for W. So there is no contribution for the W PDF. But to the element, I mean, I think there can be contribution from the electroweak sector also. So the PDFs also can change a bit, including this electric correction. So if we finally, if we want a precise result when we are including EOR and QLO and NNLO QCD electric, I mean, my thinking is that we can take mixed PDF, because when we take mixed result, we have to take mixed PDF. So QCD QED PDFs.
What do you mean by mixed? You mean take Lux QED?
Lux QED, yes, yes.
So, and
Lux
that would
QED.
be sufficient, but are they known? So at which order in QCD are they known? Are they known at NNLO in QCD, or are they only known?
They are known up to NNLO QCD QED. So,
Okay.
so they have incorporated all the photon correction in the PDF.
Also at NNLO even.
Also at NNLO.
Okay. Okay. Thank you.
Okay.
More questions? Okay. I do not see any.